Okay, thank you very much. Okay, let me remind where we are. Before, I will just change a little bit the one thing. So let's take the set of all irreducible polynomials in set of X that are primitive and non-constant. Now this set is countable, so I will just order it. So this will be Q1, Q2, Q3, and so on. So I assume that I have enumerate all possible irreducible and primitive polynomials that are non-constant. Now remember that we had this function G that goes from C to R, that was continuous, invariant under complex conjugation, and that satisfies some asymptotics. To this function, we associated some height, and we were interested in computing the essential minimum of this height. And we had lower bounds and upper bounds. The lower bound was that if I look at the sup for all, let's say, n inside the natural numbers and numbers A1 up to AN of the infimum for all set in C of G of set minus the sum from I equals to 1 up to N of Ri log of absolute value of Qi of set. So we have these numbers, not AI, sorry, R1 up to Rn. This was equal to the essential minimum of AG. So in general, it was easy to see that it is smaller or equal, but thanks to a theorem of Valais, this supremum is equal. So this is a theorem of Valais. Now this essential minimum was always smaller or equal than the essential minimum if I look at integral algebraic integers instead of just to all algebraic integers. And thanks to the theorem of Smith and Orlovsky-Zardari, this was the same as the infimum of the integral of G d mu for all mu that are probability measures that can integrate log and that satisfy that the integral of log absolute value of P of set d mu, this has to be bigger or equal than 0 for all P inside set of X. Okay, so we have this upper bound that if I look at all measures such that when I integrate log of the absolute value of a polynomial with integral coefficients is positive, so this will be a family, a convex set of measures, and I look at the infimum of all these integrals, this was always bigger or equal than the essential minimum with algebraic integers, and this was always bigger or equal than the essential minimum. So we have the essential minimum with this sandwich. Now, remember that the last day I talked about linear programming, and I brought some abstract linear programming. I was saying, okay, if we have E and F, two vector spaces, and A from E cross F to the real numbers, a bilinear form. If I have two linear functions, U belongs to E dual and B belonging to F dual, two linear functions, and we have two cones, sigma inside E and tau inside F. These are convex cones. These are linear maps. Then I can look at an optimization problem P that was the sup of the value of the linear function U of X for all X that belong to the cone sigma that satisfies the condition that B minus A of X belongs to tau dual. Okay. And then I can consider the dual optimization problem. D will be the infimum, and now B of X, B of Y, where now the conditions are that Y belongs to tau, and A transpose of Y minus U belongs to sigma dual. A small change of sign because I'm changing from the sub to the inf. These are two optimization problems, and we know that they satisfy weak duality. This means that P is always smaller or equal than D. And one of the main theorems of linear programming says that in some cases, strong duality holds in the sense, and this implies that that P is equal to D. Okay, and we give a proof that the strong duality holds, for instance, when E and F are finite dimensional vector spaces and sigma and tau are closed convex cones. Okay, and now what I want to see is that, in some sense, this optimization problem fits into this program. In principle, it's not that clear because, well, this supremum is more or less okay, because if I am looking at the supremum for all n belonging to the natural numbers, I can think that I am looking at the direct sum of R, which itself a countable number of times. Then the direct sum will mean that a vector in this space will be just a finite number of numbers, which are these guys here, R1 to Rn. But this second part looks very far from being a linear optimization problem, because I am taking the infimum of a function that I am only asking it to be continuous. So I need to massage a little bit this problem in order to make it to fit into this problem here. Now the idea is that what I can change the problem, so we want to change the problem, massage the problem. To make it as a linear problem. Okay, so the first thing we can do is that if I am looking at the infimum of a function, this can be written in a different way. So what I can do is to write this as, let's call this my primary problem. So I can write P. Now I take the supremum. As before, I can take n a natural number, then R1 up to Rn numbers. Just, yeah, I forgot to say that here I need to put these numbers to be positive. Okay, so here we are seeing a cone appearing. And then another element, lambda, any real number. And then I will take the supremum will be just the value of lambda. And then the condition is that G of Z minus the sum of R equal to, so I equal to 1 up to n of Ri log of absolute value of Qi minus lambda has to be a positive function. Okay. So you see that looking at the infimum of a function, what I can do is say, okay, I look at the value lambda that makes this function to be positive. You will see that the infimum of the function is exactly the infimum of this quantity. Okay? And now my vector space E will be just R, direct sum, big sum of all the natural numbers of R. No? This is an element here will be just lambda and then R1 up to Rn and then zeros afterwards, because in the direct sum we will have zeros here. So this is my vector space. Then the linear function is just the projection to the first factor. So U of lambda, U1, and so on will be just lambda, okay? We are having a lot of these properties. The cone is also clear, so the cone sigma will be just Ri bigger or equal than 0. And we can see that in this cone, there is no condition on lambda. So lambda can be positive and negative. Only the R's have to be positive. But I still need the second vector space and the duality between them and the cone on the other side. Okay? But what we can see is that I have a condition that tells me that this function has to be positive. Okay, what is the dual space of a space of functions? So if I want to pair functions with something, for instance, I can pair it with measures. And a function is positive if and only if the integral with respect to a positive measure is positive. So I can translate this condition into some condition, again, that it belongs to some cone. Now, since I am integrating functions that are not bounded, then I need to be a little bit careful. So I will now define P prime log of C. This will be the set of random probability measures such that the integral of log plus of set d mu is smaller than infinite, and the integral of log absolute value of q d mu is, let's put in absolute value here, is also smaller than infinite. Okay, so I want a quantity that when I plug a function of this shape gives me a true number, not just plus or minus infinity. Okay, then I will write m log of c. This will be just r bigger or equal than 0 of p prime log of c. So these are just, instead of being probability measures, these are measures that might have finite total volume. And then this will be the plus thing here. And then I will write m log of c, just m plus minus m plus. So this will be the set of signed measures that can integrate functions of this shape. And it's a vector space. So now my vector space F will be just this m log c. And now my problem P will be P is equal to the sup for all n inside, well, let's write the sup of lambda such that, and then the conditions are that the integral of g minus the sum for I equals to 1 up to n of log of Ri log of absolute value of Qi minus lambda d of mu. This has to be bigger or equal than 0 for all mu belonging to m plus log of c. And the other condition is that R1 up to Rn has to be bigger or equal than 0. Okay. And now we see that we are exactly in this shape here. The vector space F is m log c. The linear function B is just the integral of g d mu of, so B of mu is equal to this. And the cone tau is just m plus of log of c. Okay. Is clear up to now? Because then what I am asking is that my and the linear map A of lambda R1 up to Rn mu is just the sum from I equal to 1 up to n of the integral of Ri, the integral of log of absolute value of Qi d of mu, plus the integral of lambda d of mu. So this is the bilinear map. And now if you take all these things, so F is equal to m log, linear function is this one, tau, the cone is this one, and all the things I have defined here, and you write down now this the problem, you obtain exactly the problem I have written here. Okay, so now we want to find what is the dual problem. Maybe, let me come here. What is now the dual problem? Okay, so now the dual problem D will be the infimum of what? Of the other linear function that we say that is the integral of G d mu. And now what are the conditions? The conditions are that mu has to belong to the cone, n plus log of C has to be a positive function, but I also need the condition, this thing here, that A P u minus u has to belong to sigma dual, which means that the integral, so the sum of Ri, the integral of log of Qi d of mu plus the integral of lambda d of mu minus, so this is the pairing between a measure and an element of the vector space, minus u, which means minus lambda, has to be bigger or equal than 0 whenever for all Ri bigger or equal than 0. Okay? This is exactly the dual problem. Now, what is this dual problem telling me? First, I need that this thing has to be positive for all Ri bigger or equal than 0 and lambda in the real numbers. So lambda can be arbitrarily positive or negative, so there is no condition on lambda. But here, we have this term here, it's the only part that depends on lambda. If the integral of lambda d mu minus lambda has to be positive for all possible values of lambda, the only chance is that the integral of d mu has to be 1. Okay, so this implies that the integral of d mu has to be equal to 1, which implies that, in fact, my measure is not a positive measure, an arbitrary positive measure, but has to be a probability measure. So mu has to belong to p prime log of C. Now this disappears, and then my condition is that the sum has to be positive for all choices of positive numbers Ri. But if I need that the sum has to be positive for all choices of positive numbers, every of these terms has to be positive. So this implies that the integral of log of absolute value of Qi d mu has to be bigger or equal to 0 for all Qi's. And then it's like the rabbit out of the hat. This dual problem is exactly the problem we have here. You see exactly the problem we obtain here is exactly the dual problem of the problem we have here. Okay? And then it's clear what theorem we have to prove. And this is what we did. So now we have, let me, is here. Theorem with Menares, Bingham Q, and Martin Sombra. Strong duality holds in this case. Okay. So the strategy of the proof is very similar to the strategy in the finite dimensional case, but take into account that we are in an infinite dimensional space. So it's a little bit more difficult, but we are able to prove that a strong duality holds. Since a strong duality holds, we know that this quantity and this quantity are the same. Since these two quantities are the same, everything in the middle is the same. So we get two corollaries. The first one is that the essential minimum of AG is the same as the essential minimum for algebraic integrals of AG. So if you are interested in the essential minimum, there is no need to go to to arbitrary algebraic integrals, but just so to arbitrary algebraic numbers, but just with algebraic integrals, you have enough. And the second corollary, the essential minimum of AG is computable. In the sense that, at least theoretically, we have an algorithm that if you give me a precision, in a finite amount of time, I will give you an approximation of the essential minimum with that precision. Of course, possibly the sun will run out before I get this approximation, but at least I have a theoretical algorithm, and then this is the notion of being computable in theory. So in practice, it's not that clear. Questions? So at least we know that now the problem of determining the essential minimum is somewhat a manageable problem. Okay. So now what I want to do is an example of application of the results to something that in principle does not look like have anything to do with these results. Then, and in part I have to pay a little bit, I mean, I have invented to this workshop on automorphic forms and yeah, this well, automorphic and representation theoretical aspects. Now I give a hint of the automorphic aspects because I was saying that one can apply this to the study of the modular curve. Okay, that's okay. Now let's look at the representation theory aspects. So I will now start with the Grassmannian 2-4. I will start with the Grassmannian. So is the Grassmannian of two-dimensional planes in a four-dimensional space. This can be seen as lambda 2 of a space of dimension 4. And we have a nice embedding given by Plucker coordinates of this Grassmannian in P5. To write it down, the nice thing is to choose coordinates here that reflect the structure of the Grassmannian, and then my coordinates will be x12, x13, x14, then x23, x24, and finally x34. Okay, so there are 6 coordinates. So I get coordinates in P5, and they are indexed by pairs of numbers. And the embedding is given by the Plucker equation. So the image, the Grassmannian 2-4, can be seen as the set of elements that satisfies the equation, yeah, x13, x24 equal to x12, x34 plus x14, x23. So this is the Grassmannian. Now on P5, so this will be iota. On P5 I have the canonical line bundle O of 1, and I can look at Y star of O of 1 and call it again O of 1. And then I will have the powers of it, O of n will be O of 1 tensor power n. And then I can look at the global sections on the Grassmannian 2,4 of this O of n. Okay? So this for the moment looks very abstract, but in fact, this is just the space of all polynomials in Xij for I smaller than j and yeah, 1 smaller or equal than 4 is the space of all polynomials in these variables that are homogeneous of degree n, but mod out by this equation here, by x1, 2, let's call it, I don't know, S, mod out by S. Okay, so it's a very concrete vector space. Complex vector space is the space of all polynomials in the variables x1, 2, blah, 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 up to x3, 4, mod out by one single relation. Now, it turns out that this guy is an irreducible representation of the group U4 of maximal weight n 0, 0. Okay. So one can look at the homogeneous polynomials in degree n of all these variables. This will again be a representation of U4, but will not be irreducible. And here we're taking the maximal dimensional component of this guy, and this one is an irreducible representation of U4. Now, since it is an irreducible representation of a compact group, it has a canonical metric, an invariant metric, because it's invariant under this complex guy. So you start with any metric and take the average with respect to the compact group. And if I want to make it unique, I need to normalize. So I can normalize, for instance, asking that the integral of x12 to the n, so that the norm of this guy is equal to 1. So it's a unique norm that satisfies, that is invariant under U4, and that is normalized such that the norm of x12 to the n is 1. Also, it has a lattice. Namely, the set of polynomials with integral coefficients. Okay. And now, whenever one has a vector space with a metric and one has inside a lattice, like Pavlov dog, what you do is to look for the shortest vector. So we want to look for the shortest vector. Let lambda n to be the shortest vector in, let's put a name here. So this will be Rn, the shortest vector in Rn set. So the lattice will be Rn set. Okay. And now, when you have, imagine that you know what is the shortest vector, one can ask what is the norm of this shortest vector. Now, this is a completely hopeless problem to tackle to give truly a form of these guys, like counting exactly the numbers inside a circle, something like that. So it's because it can have very wild things. But we can say, okay, maybe this is too hard. Maybe we want to look at the asymptotics of this shape. What about how this grows or how this goes to 0? when n. Now, one observation is that this kind of norms is submultiplicative. So if I look at the norm of two polynomials, a times b, so a is an homogeneous polynomial of degree n, b is an homogeneous polynomial of degree m, and I look at the norm, this is always smaller or equal than the norm of a times the norm of b. Okay? In particular, this implies that this lambda n has to behave, or the norm of lambda n, has to behave more or less like some constant to the power n. We should have some exponential behavior times some error term. Okay? Since we are interested in the asymptotics, and we guess that the asymptotic will be more or less exponential and will be going to zero probably, I mean, we will be getting smaller and smaller vectors, then what one can ask, so the problem is to compute the quantity A equal to the limit when n goes to infinity of -1 divided by n of log of the norm of lambda n. Okay, and this will give me this constancy. Okay, so this is a simple problem. I want to find what is the asymptotic growth or decay of the norm of the shortest vector on this particular family of representations. In principle, this looks like a completely unrelated question, but we will see that it is related to what we have been doing during the course. Now, how can I understand this invariant metric? In order to understand this invariant metric, what we can do is to look at the line bundle of n. So this is a line bundle on the projective space and the restriction to the Grassmannian. This guy has a metric, which is the Fubini-Study metric. So remember that a line bundle means that I have a vector space of dimension 1 over each point. And this guy is moving. And then I can, having a metric means that I can compute the norm over every point. Now, a section of O of n, so S a section of O of n, I have already used it here, can be seen as a polynomial, homogeneous polynomial. So this corresponds to a homogeneous polynomial. In the xij's of degree n. And then let's call it P sub S. So the representation as a polynomial will be P, the section is S. And then the Fubini-Study norm of S is equal to, at a point xij, is equal to the polynomial S evaluated at xij, and then the absolute value of this quantity, divided by, and then is the sum of the absolute value of xij to the square, and then everything to 1 over 2, and now everything to the power n. Okay. So remember that xij are homogeneous coordinates. So in principle, they are not well-defined numbers. They are just homogeneous coordinates. But the numerator is homogeneous of degree n. The denominator is also homogeneous of degree n, so the quotient is perfectly well-defined. And this is the norm of my section S at the point given by this quantity. Okay. Now I have a line bundle with a metric. This metric is invariant under the action of U4. Now I have also a volume form, so there exists a d-vol, a volume form on the Grassmannian, which is invariant under U4. And then I can define the L2 norm of a section S just as the integral along the whole Grassmannian of this absolute value of S xij, and then d-vol. Now, since my Frobenius 2D metric is invariant under the action of U4, and the volume form is invariant under the action of U4, automatically I get that this norm is invariant under the action of U4. Hence, it has to agree with my invariant metric up to a constant. I need to normalize. So what we at the end have, let me see if I have written, yeah. At the end, this guy here has to be SL2 times a constant, and this constant is just given by the dimension of the space. So it's n plus 1 times n plus 2 to the square times n plus 3 divided over 12, which is the dimension of the space. So this norm here and this norm here are the same. Okay, it's up to an scaling factor. Now, the interesting thing is that I am looking at these asymptotics. This asymptotics is about the exponential part of the norm. This difference is polynomial in n, which means that it will disappear when I look at the asymptotics. Okay, the fact that the difference between these two metrics is just polynomial in n means that the A is exactly the same as the limit when n goes to infinity of -1 over n log of the absolute value of lambda n, but now with the L2 metric instead of the invariant one, okay? Because I am just looking at the exponential growth. Anything that is polynomial will disappear. Now, once we have this space with the L2 norm, I can consider other norms. For instance, I can consider the subnorm. The norm S sub can be defined as the sub for all x inside the Grassmannian of the absolute value of S and X ej. Okay. Now, this is a norm. It's not a Euclidean product. So this norm is again invariant under the action of U4, but it's not the same as before because this is just a norm. It's not an Euclidean product. Okay. And it is clear that the L2 norm is always smaller or equal than the subnorm. Because, of course, if I take the integral of a function with respect to a volume, of course, the volume is normalized so that the total volume is 1. So the integral will be always smaller than the max of the function. But there is an equality due to Gromov that tells me that this is smaller or equal than, let me get it straight. Yeah, some constant k times n to the dimension of GR to 4 divided by 2 times the L2 norm. So that the difference between the subnorm and the L2 norm, the error term is again polynomial, which means again that if now I define mu n is the shortest vector for the subnorm, so it can be a different one because I mean the two norms now, they are not one a multiple of the other, they can be slightly different. But in any case, if I look at the limit when n goes to infinity of -1 over n log of the norm of mu n with respect to the subnorm, this will still be A. Because the difference between the two metrics is just polynomial. We are looking at the exponential decay, hence it will not change. Okay? So my problem now is the same as looking for the smallest vector with respect to the subnorm, and then what is asymptotic of this norm. Okay. Still very far from what I want to, from the also of the previous lectures. But now we are looking at representations. So let's look at maximal tori inside my group U4. So I can now take T4 inside U4, no, T3. Yeah, T4 inside U4. This will be the maximal torus, the maximal compact torus. So it will be of the shape lambda 1 up to lambda 4 with the absolute value of lambda I equal to 1. Or maybe let's call it S4, and then I will call T4 inside GL4. This will be the maximal torus. Okay. Now, this T4 acts on my space, and hence I can write down Rn as a direct sum for all A plus B plus C plus D equal to N of B, A, B, C, D. So I can decompose my representation into weight subspaces. And now this decomposition is orthogonal with respect to the L2 norm, but also is orthogonal with respect to the subnorm. So if I want to look for shortest vectors, and I have this orthogonal decomposition, I can look for shortest vectors in each representation. And then one can say, okay, where I can find the shortest vector? Then it turns out that the shortest vector should be a more or less symmetric problem. So one expects to find it in the center of the weight space. So we can define delta to be the weight polytope. That in this case will be just the complex closure of the vectors 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, and 0, 0, 1, 1. 6 vectors. So I get this is a polytope in R to the 4, but in fact it belongs to the hyperplane where the sum of all the coordinates is equal to 2. And now, for each rational point, for each point of the form, alpha, beta, gamma, and delta belonging to this polytope here, I can look at the following thing. So I can look at phi of P will be equal to the limit when n goes to infinity, but, so this is the point P, I am not looking at all possible n's. I am looking only at n such that P times n is integral. Observe that I am taking a point P inside delta intersect with Q to the 4. So it's a point with rational coefficients. I look at all the n's such that Pn is integral. Now, I can look at minus 1 over n log of the infimum of the norm S sub for all element S inside B and P. Okay? So let me look a little bit at what I'm doing. I have a rational point in this polytope. I find an integer number n such that n times p is integral. Since n times p is integral, I know that I have this weighted space B and P. Okay? Now I can look at all possible elements in this space. And then I can look at the shortest vector in this space. And now I take minus 1 over n and take the limit when n goes to infinity. Okay? So this is a function on my polytope space. And this function, one can prove two things. First, that it is a concave function. This comes again for submultiplicativity. One can show that this function is convex. And one can also show that it is symmetric under the permutations of the vertices. Okay? And we can also see that here I am looking at the minimal vector of the weight spaces. And then I am taking a minus. So I am looking in some sense at the maximum. And I can see that my problem A, the thing that I am looking at, is exactly the sup of my function phi. Because I know that the shortest vector will be in some weight space, and then I have divided by this. But now, imagine that you have a function which is concave and symmetric. Where is the maximum? Has to be in the middle point. There is only one possibility. So which implies that the sup is in the middle. The sup is in the middle. Wait. Okay, so now my problem is so now A is equal to the limit when n goes to infinity, again of -1 divided by n of the infimum of the norm of S, the norm of S sup for all S belonging to the weight n. Okay? But not completely, because if I look at weights n, I get a polynomial of degree 2n. So I have still to divide by 2. So I have to scale a little bit because of the homogeneous polynomial. So I am reduced to look at things in middle weight. Okay. Now, let's take the direct sum for all n of b, n. Now this is a much more manageable ring than the ring of direct sum of all Rn. And in fact, this is a ring which is generated by just two elements. Let me write which one I have chosen. Yeah, x1, 2, x3, 4, and the polynomial x14, x23. Okay, so observe that having weight n means that I need monomials with all the numbers here. So because the weight is the degree of the number of ones, the second is the number of twos, and so on. I have 3 monomials that can generate, but I have one equation, which means that with only 2 monomials, I can get all the rest. So I get a polynomial, so a polynomial ring, which is generated by this guy. I can look, let's call it, I don't know, big S. I can look at prog of S. And since this guy is a polynomial ring generated by 2 elements, it turns out that this guy is just P1. Okay? Now, this ring here is contained in this ring here. And you know that whenever you have a map of rings, you get a map of spaces in the other direction. So we have a map that GR24, but only a birational map to P1. And this map can be seen as a GIT quotient of GR2 by the action of a 3-dimensional torus. So in some sense, this maximal torus that was acting here, in fact, it is a 4-dimensional torus, but only a 3-dimensional part of it acts on the space. Because you know that in projective equations, if you multiply everything by a constant, you get the same result. So only the part of determinant 1 acts. So we have a torus of dimension 3 acting on this guy, and the GIT quotient is just P1. Now, when we have a GIT quotient, and this guy has this line bundle of 1, we automatically get a line bundle in the quotient, whose pullback is the original one. And if I have a metric here, I automatically get a metric here, which is called the Kempf-Ness metric, which is just at every point here, you look at all candidates, and the supremum norm of all candidates. So we get in of 1, so here we have a O of n, if you want, which corresponds to the O of n here. And now the norm of a section S, the Manford-Kempf, the Kempf-Ness metric at a point X is just the sup for all y's such that this is pi of y is equal to X of the norm of S at the point Y. Okay, so we get a norm here. And the good thing is that in this case, this norm can be computed very explicitly. And in fact, yeah. So the computation is in the notes, but the end result is that the norm of X 1, 3 to 4, X to 4, at the point set 1 in P1, this can be computed very explicitly, and is just 1 divided by 2 times 1 plus the norm of Z plus the norm of 1 minus Z. So I get a line bundle on P1 with a very concrete and explicit norm. And by the construction of this Kempf norm, it is now easy to check So now we have this norm. Now to this norm, so I will call minus log of the norm of this section x 1, 3, x to 4. I will call this g. And this is just log of absolute value of 2 times 1 plus absolute value of z plus absolute value of 1 minus z. This is a function of the shape we have been studying up to now. So I can define my height function. And one can check, in the notes is the derived argument, that the problem I am looking, A, is exactly the essential minimum of this AG. So we have converted the problem of finding the shortest vector of our representation, thanks to the symmetry that has been allowed me to reduce the problem from the Grassmannian to P1 to the problem of finding the essential minimum of a particular height. Okay, good. So now one can try to guess, and for instance, I ask ChatGPT what should be the shortest vector, and then he said, oh, possibly is the most symmetric one. So one clear candidate always is to look at the most symmetric guy. So let's make a guess. If I look at the polynomial x12, x13, x14, x23, x24, x34, so here is the most symmetrical one to the power n. So this is a guy of dimension of homogeneous degree 6n. So I can now look at the limit when n goes to infinity. So let's call this guy, I don't know, u sub n. I can look at the limit when n goes to infinity of -1 divided by 6n of log, or maybe b6n, of log of the norm of b6n. And this quantity can be easily computed, and it turns out to be 0.8957, and so on. Okay, and this is a first candidate of the shortest vector. But now we have a lot of tools to check what is essential minimum. So we have tools to get lower bounds, and we have tools to get upper bounds. And also we have a very nice symmetry that will allow us to go very fast. In the sense that if you look at this function has a lot of symmetries. So if I change z by 1 minus z, I get the same function. And if I change z by 1 over z, I also get the same function. So I have a 6-fold symmetry. Well, sorry. If I change z by 1 minus z, I get the same function. If I change z by 1 over z, I get the same metric, but not the same function, because this function is related to the point at infinity. And if I change set by 1 minus z, the point of infinity goes to the point 0. But in any case, the problem is the same. So the essential minimum is invariant under changing z by 1 over z. So I have, oh, sorry, maybe I have to rush. So since my time is over, then I have to send you to the notes. And using all the techniques we have been using before, but just the barely scratch, what we can show is that A is always bigger or equal than, 0.90753 dots. Hence, my guess was wrong. And I get an upper bound of 0.90785. So even if we cannot compute exactly, just with the first easy bounds that we have constructed, we can see that the A is between these two quantities. So observe that at least we have 3 significant digits. The error is in the 4th digit, and it's very far from this wild guess one. And you have in the notes the argument to get these ones. Okay, thank you for your attention.
Thank you, Doc. Any questions, comments, remarks? Okay, so maybe I have a question. So you, I mean, I'm aware of this Scholz's functor from, if you take this bi-Hallstatt from the Shimura curve for genus 2, and it will land inside this G hat plus 1 into 4. So if you take a principal polarized, so all your computation, can you say something about the stable faulting site of the each individual principally polarized abelian variety? So you have this map Hallstatt using Hallstatt period maps.
It's a good question. I have not thought of it, but maybe we can think about it and see if we can get something out it. But what will be the invariance of these quantities? I mean, because here we are using very strongly that we have this 3-dimensional torus that is acting in a 4-dimensional variety, and then the quotient is 1-dimensional, and it's big 1. So I can use all the tools coming from this big 1 because we have been studying big 1. Now, my postdoc Q with a friend, they are extending this to arbitrary curves. And we are thinking how to extend this to arbitrary varieties, because in some sense, the lower bounds, they work for arbitrary varieties. The upper bounds, some of them work, but they are not so easy to handle. And then we are working on doing this. And then maybe the problem is that if we are lucky and your problem can be translated to a problem in P1, like for instance, for the modular curve, we know how to compute, how to approximate the essential minimum of the faulting heights of elliptic curves. This can be done. And we can approach it quite well because the modular curve in this case is P1, or we can reduce everything to a computation in P1. If your problem, so if you at the end your modular variety is a different thing, you will have to wait until we have worked out how to work with more general varieties.
Any more questions, comments? Thank you very much.